Yeah, here it is. Here's the compare, just before the jump, which is the same thing, but without the name. And eventually here's the actual one. And if I follow this jump, you can see here that we are working on the address. Where am I? Here. I'm working on this address, 160, which is not the DLL address at all. This is code that is being copied and modified and obfuscated on somewhere else. So if I follow the jump, I end up in the DLL. I have all the code of the DLL because this is like an internal, like a whole dump of the address space of the process. So I have everything that was used by this process. So I can actually see the code of the DLL. So you can see this is the same address as we have in the DLL, the 54C. So this is what I was saying about the references that are still kept. And actually later on, within the obfuscated code, we get a call to a function in the DLL. And if I go here, that's exactly the same as this one. These two functions should be exactly the same. Or I got the wrong one. How many calls are there? Ah, no. It's this one. I went ahead. Yeah, with a little bit of imagination and with our names, you can trust me. That's the same one. So that's how the obfuscation looks like. As you can see, Tomato does a quite good work making things look bad. So let's keep going. So, summing up a little bit what we saw up to now, the battle between packing and unpacking is like, I have some friends that are still trying to do like perfect unpackers that reconstruct like the original EXE, and I just think that's kind of a little bit of a waste of time, because with the hardest packers, the application is modified in such a way that I think is extremely hard to consider that you will be able to restore the original application, like the original binary. I think that that's something that eventually, if the packers advance enough, won't be possible. It doesn't mean that you can get something that could eventually run or it can be easy to analyze. That's another thing. But I'm not anymore aiming at getting an original EXE with a nice import table. I'm more for getting a working dump with simples. That's all I need usually. So I think that can be done, and that will be possible for a long time. I guess even with virtual machine techniques, you can do quite a bit of things with the scripting and optimization working on a dump. So I think generically all of these can be done. Like I'm writing generic unpackers for quite a while, and I don't see many problems that I'll be able to do it in the future. I see some technical battles, but I don't see that it will become impossible to do. Reconstruction, yes, reconstruction can be, it is a mathematical problem to reconstruct something that has been extremely obfuscated into an original form or a reduced form. Can be optimized, but I mean, reconstructing it back to the original form, that's another thing. So I will say that yes, you can get close to an original form of the code, but not necessarily restore the original application. And now I still have some time, we can have some questions, but I just like to cover this. This is really recent, like a couple of weeks ago, Escape mentioned a technique against generic unpackers, or some heuristic that generic unpackers use. And the heuristic is the one of tracking dirty memory. And a basic way of displaying this would be like originally when the unpacker is going on, when the unpacking is writing to memory, you get like a virtual address, then the code is written, that will be the second block. The code is written, and eventually execution, that will be that arrow coming to the written block, that will be the execution going there. So that's basically the algorithm of an unpacker, very basic unpacker. You know, just get the memory, you start decompressing or unpacking the application there, and eventually give it the execution. So you can actually track for this. That's what lots of generic unpackers do. They try to monitor the memory whenever see that the execution goes to dirty memory. It's like, ooh, that's interesting. You can do a bit more advanced heuristics because this is not totally foolproof, but you know, it works. So what he did, and that's a really cute idea, I believe, was using the memory mapping unit abilities, or like what Windows provides, you can actually map two virtual address ranges to one physical memory address range. So you would have two different address ranges within your user mode application that map exactly to the same physical memory. So you could actually write to one of these and execute from the other. So you will break this heuristic of detecting, because you will be writing to some area of memory, which could be anything, it could be data, and there will be never anything executed from that area. You will be executing from another area, but all of these are the same. These two things are the same. So any modifications you do to the one appear in the other. But this is really cute because it breaks this technique. But if you are playing at a high enough level, if you're working at a kernel level, you can actually study the page directory like the Memorize tool, and I see that there is double mappings and things like that, which are not necessarily a standard thing for most applications. So that would ring something like, there's something weird going on. So, and low-level emulators, anything that gives you access to the memory mapping unit to be able to detect these things, but still most of, or all of the user mode generic unpackers would be tricked by, that use this technique would be tricked. So I found that really, really cute. And one last thing that I want to show before I jump into the references is like talking about visualization. Just to give you an idea of the complexity of like a Temaida when it's running in memory. Let me show you if you can see this properly. First, let me explain you what you're looking at. This is a representation of a memory dump of the address space of a process when it was unpacked. So each of these blocks is a memory page, is 4 kilobytes. The color and what you will see now, the height, is the entropy. So the higher or the redder the color, it means that it's more likely to be code, for instance, or is to contain high entropy data, which usually either is code or is some sort of compressed data. So this was Notepad packed with NSANTI. And if you can see the pointer, actually Notepad is just this thing over here. The actual code is just those things. The rest is just like heap and stack. So just to get an idea of the whole layout. I mean, here we can see the higher points. The red points are the ones with the highest entropy. So these will be where compressed data might be. The rest that you can see is all over are areas containing different sets of data. Could be text, could be just random, arbitrary data. So this is NSANTI. This is Notepad. Now you're going to see Notepad with Temaida. So Notepad is still that thing over there. The rest is Temaida code, obfuscated code, temporary code of the virtual machine protected malware. So again, you can see this is quite a monster. It turns an application that is like 60 kilobytes into something that's like 1.5 megabytes, and most of it is Temaida's own code, and obfuscated code from the API. Remember that it will pull APIs, put them in this address range, obfuscated. So that's what you're looking at. So that's the level of complexity in packers that we're seeing nowadays. So with techniques like virtual machines, techniques like hardcore obfuscation and flow obfuscation, anti-analysis techniques, it's going to be much more work for us, I think. So after showing this, I think I just want to quickly walk through the references. Whenever you get the slides, whenever they're on the site, I put like 4 slides in the end with the references. These are really worth a read if you're interested into this. Really good papers on malware analysis, on virtual machine analysis, virtual machine detection, Escapes article, Vorislau paper on virtual machine virtualization techniques, extremely good. Rolf Roll's articles in OpenRC, really, really good about using optimization techniques against virtual machines. Then Orient site for Temaida, they have some technical info about the thing. Rewolves, that's x86 virtualizer, that's the thing in OpenRC. If you like to study virtual machines, really good thing to check. And if you want to read more about nanomites and you can read Serbian, then I would recommend you the Rocco's nanomites write-up. Use Google Translator if not, that gets the work done. And then Memorize, that's a kick-ass tool that he wrote as well with his team. So that's another thing you got to check and try because it's going to help you to do lots of these things. And well, I think we have 5 minutes left. I would like to thank the Hack in the Box team and Dylan and everybody that came here. I hope you enjoyed. And if you have any questions, please fire.
Any questions from the floor?
Was I that good? Yes.
As usual. Well, thank you very much, Ero. Thank you for taking the time, and we really appreciate having you down here.